Hi, everybody. Thank you for joining Synthetic Intelligence Forum. My name is Vic, and I'm your host. I'm very happy to welcome to the feed today Mark Coletti and Siggy Scott, who are the co-originators and co-developers of Leap, which is a library of evolutionary algorithms in Python. Very happy to have them joining me today. I'm going to add them to the stream, and I'm also going to add their slides to the screen. So welcome, Mark, and thank you also, Siggy, for joining us today. And the floor is yours. Take it away. Thank you.
All right. Thank you, Vic. Thank you for inviting us to speak today. So my name is Mark Coletti. I am a research scientist at the Oak Ridge National Laboratory in eastern Tennessee, and my research focus is on evolutionary algorithms. Particularly, what I'm interested in are the challenges associated with scaling up evolutionary algorithms to run on big machines. For example, our Summit supercomputer at the Oak Ridge National Laboratory.
And I'm Siggy Scott. And so both Mark and I work on applications of artificial intelligence to problems for the US government at our respective national labs. And in particular, as Mark mentioned, we tend to work a lot with applications of evolutionary algorithms. So what we want to talk about today with you all is this idea of evolution as problem solving and how this set of tools fits into the wider artificial intelligence and machine learning space.
So once you have a sufficient background on evolutionary algorithms to provide context for the rest of the talk, we'll next talk about the library for evolutionary algorithms in Python, or Leap. So what we're going to do is we're going to describe what Leap is. We're going to go over a bit of how to use it, and also do a little bit of a deep dive to show you how Leap works underneath the hood. And along the way, we're going to give you some live demonstrations for use cases, and we'll finish up with a couple real-world examples of how Leap is actually being used now at the Oak Ridge National Laboratory. Next.
All right, so to get started, I want to back up and talk a bit about artificial intelligence so we can get a view of how EAs may fit into that wider scheme. So there's a lot of ways to look at AI, of course. One way is to focus on the problems that it aims to solve. And I think it could be argued that there are three main or big classes of problems that artificial intelligence is traditionally preoccupied with. So one is to predict a variable. So this often takes the form of a regression problem, often a complex high-dimensional one, or a classification problem, like we see so often in computer vision or natural language processing. Second is to control a system over time. So kind of the ultimate examples of this perhaps are robotics and self-driving cars. And then on a more broad level, there's optimizing a function. So this can mean a wide variety of things, but one example might be to optimize the topology of a mechanical part to maximize some desirable properties in an engineering application. So I think that any definition of artificial intelligence is on some level wrong, but that this is a useful one, that AI is a collection of mathematical techniques built for especially complex prediction, control, and optimization problems. So now the question is, so how do evolutionary algorithms, as one of many different paradigmatic approaches to AI, fit into this wider set of goals? So the first way to understand EAs, I think, is to see them as an extension of the old idea of intelligence as heuristic search. This dates right back to the earliest days of AI and has gone through many modern reinventions. So the basic idea here is that when you're solving a problem, you can imagine and define a large search space of all the possible solutions to your problem, some of which will be poor quality and infeasible. And then the obvious observation is subregions of this space will have higher quality solutions than others, right? So some predictive models are better at, say, detecting faces than others. Some control systems are going to be better at a self-driving task than others, and so on with a mechanical part. So evolutionary computation and the evolutionary algorithms that it studies is a modern view that views artificial intelligence through this lens of search. And this raises a number of natural questions that go back to the earliest research in AI, such as how can we intelligently zoom in on high quality regions of a space as quickly as possible? And on a more technical level, how do we do this in a way that lets us exploit parallelism so we can use the big distributed clusters for scientific computing that are available today in an informed way to take our prior domain knowledge that humans have and bake it into an algorithm so it works better, and so on and so forth. So another way to look at this search space characterization of problem solving is to draw a function over top of it like this that represents our quality or maybe our error of a predictive model. And then the problem of search is very, very closely related to the problem of optimization, finding the point of lowest error, for instance, in a machine learning model. And at this point, you might stop me and say, okay, well, Siggy, I know enough to know there are lots of traditional approaches that let us solve optimization problems of various kinds, such as gradient descent. And gradient descent is the workhorse of machine learning today for a good reason. It effectively lets us directly ask our algorithm to, hey, just move me toward a better answer incrementally by using the differential calculus to compute a gradient, which allows us to almost literally slide down the error hill towards better solutions as the system learns to get better at its task. Other approaches include things like quadratic optimization or convex or conic optimization. These are even better because they allow us to ask the algorithm directly to, hey, just solve for the right answer, often in polynomial time. If our function that we're trying to optimize is convex, if the matrix defining it is positive definite, and so on and so forth. So the theme I want you to recognize here is that a lot of these traditional approaches to solving problems of this kind are limited by the assumptions they make. You can't apply gradient descent if you can't compute a gradient, and so on. And in particular, we often don't even have an algebraic representation of our problem in many, many cases, especially complex applications, making it very difficult to apply these methods, especially not directly. So the evolutionary conception treats this a little differently and says, let's not assume that we have an algebraic kind of mathematical understanding of the problem necessarily, but instead let's focus on sampling and then an iterative process of variation and selection to make progress in solving problems. So this first step of a typical evolutionary algorithm, or EA, is to randomly sample a set of solutions from across the space. Most of these will be very poor because they were just randomly constructed. And then the next step is to perform selection, which means choosing some of the best individuals in this population. And then variation, so this applies perturbations like mutation, or maybe an operator that combines two individuals and kind of gives their intermediate as an output or something like that. Then we'll typically discard the parents and then repeat the process. We select good individuals, variation, discard the parents. And what you can see here is the evolutionary approach begins with what is initially a very broad exploratory sampling of this solution space. And then when it's successful, it can very quickly, in just a few iterations, zoom in with a sort of killer instinct on higher quality regions of the search space. And because it does this while making very few assumptions about the structure of your space and of the function that you're trying to optimize, it's an extremely widely applicable technique. So yes, we absolutely use evolutionary algorithms to solve robotics tasks and robot control tasks, but also things in problems where it may be difficult to even know where to begin defining a function and a gradient. So I have a colleague that has applied evolutionary algorithms to configure the parameters of enterprise search engines like Apache Solr or Elasticsearch, because there's a lot of different parameters to tune if you want your enterprise search to work well for your organization. Another big one is neural architecture search. So we all know that gradient descent is a very effective method that's at the core of tuning the synaptic weights of neural network architectures. But if you want to search for the space of architectures themselves for high-performing ways of arranging your network, evolutionary methods are one of the leading approaches to approaching that problem. So here's one concrete example of an application of evolutionary algorithms that's been getting a lot of attention in recent years. So the satellite constellation design problem, you can probably imagine just by looking at this figure, has quite a bit of complexity to it. At the basis, astrodynamical systems are nonlinear systems that have a lot of interesting behavior, especially once you perturb the satellite from its planned orbit. But also there's combinatoric issues here of how many satellites do we need to perform a particular mission? How do we organize their orbits so that they can collaborate together to solve a task? And then another complexity that arises here is constellation design problems are typically highly multi-objective. So we typically care about one objective first, geographic coverage, because most satellites interact with the surface of the Earth through radio waves or something of that sort. But then there's a lot of other concerns. Your classic swap-C that arises in any aerospace design problem: size, weight, power, and cost. And many more of these that vary by mission. So as we enter kind of this new phase of what they call proliferated low Earth orbit, where we are launching not just 3 or 4 satellites, but potentially thousands to complete a single mission, these problems get more and more complex. And evolutionary algorithms have turned out over the last 20 years or so to be really the only class of approaches that can really handle these multiple conflicting objectives in large numbers, and looking for the trade-offs between different design decisions that are available to the designer. All right, so now we're going to transition to the second part of the talk, where we're talking more concretely in an applied way about LEAP. So up to this point, we've talked about evolutionary algorithms on a level where we're trying to inspire you to think about what EAs are and about what kind of problems you might be able to use them for in your work. LEAP is our effort to build a Python framework that makes it as easy as possible to create a wide variety of evolutionary algorithms and apply them to new and complex problems. So LEAP's history goes back to around 2004, when our colleague Jeff Bassett started piecing together an EA framework in an early version of Python. And a few years ago, he came to Mark and I and said, hey, could you help me update this code to Python 3 so it will work with, the latest and greatest? And when we started looking at his initial version of LEAP, we realized it had some really nice design properties. And we realized this was the basis of something that could be of value to the wider community, in the same way that, say, Keras or TensorFlow and PyTorch have become valuable to the neural networks community. And so we decided to develop this into something that we hoped could fill a similar niche for the evolutionary search and optimization community. So what we find as we work with a lot of our colleagues in academia and industry is that at first, you don't need a framework. This is true for neural networks too. If you want to get off the ground with a very simple kind of classroom level experiment that will give you some kind of iterative process that makes progress on your problem, then copying and pasting some code from Wikipedia and piecing it together in your own ad hoc solution is good enough. But what happens is the moment you need a little bit more complexity or a little bit more industrial strength, a project will often slow to a crawl, because as you need the mathematics that come with more advanced algorithms or distribution across HPC clusters, you can really start to benefit at that point from using a reusable general purpose toolkit. So when we started thinking about how to build LEAP into a general purpose toolkit that could meet the needs of the community, we found ourselves thinking of the user base for these kinds of algorithms in terms of 3 stereotyped roles. So the first is the engineer. So we conceive of the engineer as somebody who has some other problem that they need to solve. And so they may prefer to have a quick and dirty solution at first, but then eventually may have need for more advanced industrial strength features, such as high performance computing support. Our second role is educators, who have a bit of a different set of needs. An educator might emphasize the need of really good documentation and tutorials so they can get students up to speed in a framework quickly, or visualizations and examples so that the classroom can be turned into an environment where you can demo algorithms and play with them and learn by interaction with their parameters. And then the third role is the researcher. Researchers are people who want to push algorithms in bold new directions where no human being has gone before. And what they tend to care about is having a reusable framework that lets them compose existing components, maybe well-researched components, to build new systems rapidly and easily. So looking first at the engineer's view, this drummed up for us a few requirements. One is that quick solution that I mentioned earlier. One way to interpret that is if you need just a quick and dirty algorithm to solve a problem in kind of a known domain, then you should be able to do it with one line of code. But then once that's not enough for you, you're going to want, once you need something more complex, you want to be able to configure it in a concise way in one place without your changes being spread all over your code base. And you're going to eventually have need for more advanced features such as distributed evaluation. So with that in mind, here is what the easiest bare bones way to get started with Leap looks like. First, we import our leapec.simple package. This is available in the Python package repository, and this EA-solve function. Then we're going to define a function. This is what you would define to characterize your problem in terms of a fitness value that you want to maximize or minimize. And then since functions are themselves first-class objects in Python, like many programming languages, we just now pass that function directly into our solver. So this kind of interface can get you up and running really quickly. For example, in a continuous optimization problem, that's what we have it configured for here. But very rapidly, we find that a single one-line interface like this limits you and kind of puts a straitjacket on how flexibly you can configure an algorithm like this or make it do new things. So after this one-line interface, we wanted to design a next layer to keep things as simple as possible, but also provide maximum flexibility in the framework. And to do that, we took a step back to think about a unified picture of evolutionary algorithms and what it would take to design a good reusable framework that would encompass as many of them as possible. So if you've studied evolutionary algorithms before, most introductions will introduce you to the three big historical families: genetic algorithms, which have the most name recognition; evolution strategies, which have also gotten quite a bit of press recently; and evolutionary programming. And traditionally, these were treated as three kind of distinct classes of algorithms, and you were either using one or the other. But today, the research community has come to view these more as geographic silos as much as anything else. Genetic algorithms were invented in Michigan. Evolution strategies came out of some engineering applications in Germany. Evolutionary programming was from UCLA. So these communities reinvented kind of the same basic idea at much the same time, because good ideas often tend to be reinvented multiple times. And today there are many other families. John Coe's genetic programming is very famous. Estimation of distribution algorithms. These include things like Bayesian optimization, which if you squint just right, can itself be seen as a kind of evolutionary algorithm. Particle swarm optimization as well fits into our selection and variation framework. So all of these today tend to be referred to by people working in these areas as evolutionary algorithms. And this more general term is preferred, even though terms like genetic algorithms are still popular. So what we did is took this unified view of evolutionary algorithms that's been developed mostly by Kin DeYoung as our starting point. And we realized that thinking in this kind of, in science, there's splitters and clumpers. Splitters tend to see the differences between things. Clumpers tend to see the similarities. Well, we found that looking at the similarities across these approaches gave us a very nice way to design a flexible framework for organizing our code around. So it ended up having very practical use for us. So let's have a look at the framework that we came up with after thinking through this. It has three main parts. So in our view, almost any evolutionary algorithm will have a problem. So this is that function that you're trying to optimize, a way of comparing two function values. A representation, this defines your solution space and also how you transform solutions into something that can actually be evaluated on your problem. So how do you create a neural network out of a string of weights, for example? And then three, very important for evolutionary work, is the operators. These are your variation and selection operators that produce new solutions out of old solutions via some kind of mechanism. So there's quite a bit of diversity in the different types of operators that get used in different algorithm families. So we put kind of a lot of thought into this part of the framework. But at the end of the day, these become the components that a researcher will look at and say, I can see in this mathematical description, here are all the different Lego blocks that I can invent and put together to generate new algorithms and to solve new complex problems. And at a high level, what emerges out of this is this old idea of a MetaHeuristic. MetaHeuristic methods, which include evolutionary algorithms, have a few different interpretations, but we tend to view them as a template that you fill in. So it's a high-level view of an algorithm that you choose the components for to create a more specific algorithm. So here's what a MetaHeuristic looks like in Leap, and this is kind of the framework's signature, is this way of laying out an algorithm. So first you'll notice we're still calling a single function, but this time the function acts as a MetaHeuristic, and we pass in those three main components. We pass in a problem. This one's just a simple fitness function over Boolean vectors, and then a representation. This defines how we initialize the initial population, among other things. and then that pipeline of operators that generate new solutions from old ones. So here we have a selection method, some variation operators for mutation and crossover, and then we evaluate the fitness of the new population and pull it all together. So the output of this code might look something like this when you run it, printing the best known solution at each iteration to the command line. But one advantage of this list of operators that we have in our operator pipeline is you can add elements to that pipeline list to add things like visualization or statistics collection if you need to collect data for an experiment or things like that. So I'm going to jump into a quick demo here to give you a sense of how that visualization works and things that Leap can be used for. So first on the left here, let's look at an NP-hard optimization problem. Specifically, we're going to look at a nonlinear integer programming problem. So here I've switched over to my IDE. We're looking at a Python example file that ships with Leap if you take it out of its GitHub repository. And you can see in the main block of our program, we're calling, as on the slide, that generational EA MetaHeuristic and passing in the three main components, its problem, its representation, and its pipeline. What's new here is that at the end of the operator pipeline, we're adding in a few extra operators that we call probes. These are operators that don't modify the population, but just collect information about them and optionally visualize them. So the first two probes will collect some visuals. The third probe is going to write some statistics in comma-separated value format to standard out so that you could do some data analysis on it. All right, let me pop up my terminal here, and I'm just going to run this example. It's an examples int rep for integer representation. And the first visualization here is the best of generation fitness curve. In this case, we're minimizing, so lower is better. And it's jittering around a lot now because of the stochastic nature of evolutionary search. And then here on the left, we have a visualization of the actual population on that search landscape. We're solving a nonlinear optimization problem, so it's kind of a rough landscape. What you'll see is this population sparkles around the solution space. It tends to gravitate towards these circular regions, which have the better fitness, in this case, lower objective function value regions. But it will also explore a lot of the rest of the space, because like in several branches of AI, in an evolutionary algorithm, we want to see, or any metaheuristic, we want to see a balance between exploratory behavior and exploitative behavior so that it can search for high quality regions of the space. All right, so let's close this down, and I'm going to hop over to another example of robot controllers for something a little bit different. So in this case, we have the same metaheuristic, but it's parameterized differently now. We're passing it in a problem that actually acts as a wrapper for the OpenAI GYM environments, which is a popular benchmark used in the reinforcement learning community. And then we give it a representation. This time it's a real valued vector. But we're also passing in a decoder object, which, long story short, converts our solutions into neural networks that can actually be executed. And then we have a pretty standard operator pipeline with some visuals. So let's run this one. Neural network cart poll. What's going to pop up first here is the OpenAI provided simulations visualization. So this is the cart poll problem. It's a classic kind of hello world problem used in optimal control theory and reinforcement learning. The goal is to control the motion of the cart, the black box there, to keep that poll balanced. It jitters a lot here because as soon as the poll starts to fall, the simulation resets. Now, the visualization kind of slows down the algorithm here. So I'm going to switch a flag in my code to false to turn off that visualization. And then we'll run it again, and we can see the progress of the algorithm. So here we're seeing the best so far known neural network controller for cart poll. And then we have our best of generation fitness on the left. This time we're maximizing fitness because we want to maximize the amount of time we can keep that poll balanced. If you look closely at the neural network, sometimes you'll see the thickness of the lines change as the best known neural network is replaced by a new best neural network. So this is an example of a problem where you could do this with gradient descent, right? Reinforcement learning has for many years been using policy gradient approaches to apply gradient descent to these problems. Evolutionary methods have some advantages, though. In particular, they've been much lauded for the ease with which you can parallelize and distribute the learning process over many nodes on a distributed cluster. So there's a lot of research ongoing right now on how to hybridize evolutionary approaches with traditional policy gradient approaches to kind of get the best of both worlds. All right, and now I'm going to hand the baton over to Mark, who will talk a bit about our distributed evaluation facilities in LEAP and the applications that we've been looking at.
All right, thanks, Siggy. So the intuition is with evolutionary algorithms is that they're embarrassingly parallelizable. In other words, imagine this. You've just created a whole generation of offspring that have to be evaluated. What you could do is you could scatter those off to their own independent computational resources to be evaluated, whether it's an individual core on like a laptop or a node on a local network or even a node on a supercomputer. So they're independent of one another, they can all be evaluated, and when they're done, they're all gathered back together as completely evaluated individuals to be incorporated into the population and be prospective parents. Here is the problem with that approach, is imagine that you have a generation of offspring that are being evaluated. You cannot proceed to the next generation until every single one of those is evaluated. Now further imagine that some of those individuals, those offspring, have been evaluated much sooner than the other ones. Their associated computational resources are going to sit idle until the next generation. And this is particularly egregious if you're, say, scaling up on ORNL's Summit supercomputer, because it's a valuable machine and you want to make the best use of the resources you have available. So what's the solution for that? The solution is to make a little bit of a tweak to the evolutionary algorithm. You would use something called an asynchronous steady state evolutionary algorithm, which is depicted here. So on the right is the sort of laid out and detailed how the that particular evolutionary algorithm works, and on the left is sort of a cartoon of that. And I'll just walk you through real quick what the cartoon is. So imagine that we're tuning the hyperparameters for a neural network, which is depicted in those little neural network diagrams. So the silver ones are ones that have already been evaluated, the red ones are being evaluated. So you have a population that's being constantly updated at the bottom as that pool of individuals, and you have the various resources depicted as GPUs at the top that are evaluating offspring. So now further imagine that one of those computational resources is done evaluating an individual, which is shown on the left. So now you have the candidate to be inserted into the pool. So what you do is you take the most fit individual currently in the pool and that candidate, and it's sort of like Thunderdome. You bring in two, one of them is going to be the best, and that best individual is going to be inserted into the population and the other one is discarded. It's almost like the reality show Survivor. So one of them gets to be voted on the island and one's voted off. Okay, well now you have a problem. You have a computational resource that's now idle, and you can't have that. So immediately you select randomly a parent, you clone it, and you zap the clone, you mutate it in some way. So now you have a brand new, never seen before prospective solution to your problem, and you assign that to that freed up resource. And you just keep doing that in parallel, and hopefully you can see that you make a far more efficient use of your computational resources than by traditional by-generation approach. Next. So here's how LEAP supports that. So this is another MetaHeuristic, and it looks very similar to the one that you saw before. And unlike generation, it's not called generational EA, it is literally called asynchronous steady state. Next. And how it works under the hood is we use the third-party Python package called Dask. And so we rely on Dask to actually farm out and distribute the evaluations. And what's nice about Dask is it scales. It can actually do the evaluations in parallel on your laptop all the way up to the Summit supercomputer. And what's nice about how we have things set up is that LEAP doesn't care. It's completely agnostic. It's going to treat it the same way whether you run it on your laptop or whether you run it on Summit. Next. So the first set of parameters is going to look a little bit different. You're not doing things by generation. So you have a budget of bursts and not generations. You can dictate the size of the different populations. And like before with the other MetaHeuristics, you have to select a particular problem that you're trying to solve. Next. And also, like with the other MetaHeuristics, you have to specify a representation. So like before, a decoder and how you're going to initialize the population. And optionally, you can define another class. In this case, we have an optional subclass you could use called distributed individual that adds some additional housekeeping. For example, what distributed individual will do for you is it will stamp each individual with a unique UUID that you could use to name file names for output of models and so on and so forth. Next. And like before, you have this pipeline thing. In this case, the pipeline is the recipe for how you create these new offspring to assign to a worker to be evaluated. So you just, again, select somebody randomly from that population that we saw before. We clone it. We do a mutate bit flip on it, because this is a binary problem that we're using. And the pool operator, the last operator, is the driver for this. And we just say we just want one individual because we have only one resource that we need to assign an offspring to. Next. And the last two are optional parameters, and these are callbacks. So the first one is a callback function that's invoked every time an individual is done being evaluated. And that might allow you an opportunity to append, say, to a CSV file, each of the individuals that comes off the assembly line, so to speak. And the population probe basically does a snapshot every so often of that population, so you can track that and say in a separate CSV file if you wanted to. Next. So we already talked a little bit about support for educators. And again, if you're an instructor, you want to teach, you have a module for teaching evolutionary algorithms, you want something that's easy to understand. You want to have a lot of examples. You also want to have some tools that allow you to play around with code and visualize the output. And Leap comes stock with several Jupyter notebooks that actually can serve that purpose as a base for class exploration. And you saw some of the examples that Siggy showed, and there's plenty of other examples that also could serve as a basis for a classroom instruction set. Next. So I am a researcher, and my needs are a little different from an engineer and from an educator. So we have strange needs for a general framework for evolutionary computation, and we, in a sense, kind of push it to its limits. For example, we may want to explore the effects of a new operator we came up with. Next. So here is an example of some other probes that maybe you could take a snapshot of an individual before and after, say, an operator. So instead of a mutate bit flip, maybe I invented a new operator and I wanted to see sort of the before and after effects of that operator on an individual. Inserting these probes facilitates that. And I can tell you from experience, being able to implement something like this when some of the other evolutionary algorithm toolkits is difficult to do. And this is one of the many motivating reasons why we developed Leap, is basically to support something like that for evolutionary computation researchers such as Siggy and myself. Next. So Leap comes with a number of benchmark functions. Next. That if you're an evolutionary computation researcher and you come up with an evolutionary computation or an evolutionary algorithm variant, there are some standard benchmark functions that you could use to exercise your evolutionary algorithm on. And so Leap comes with just a whole plethora of standardized benchmark functions that are familiar to the evolutionary computation community. Next. All right. So now you guys are all experts on how to use Leap. Let's take a peek under the hood, because I'm sure especially some of you software developers are interested in how this works. And particularly this pipe thing. Next. So let's talk about pipe, because this is the heart of how Leap works. It relies on a third-party Python package called toolz that actually supplies some functional programming tools and some iterator tools. And for those of you who are familiar with the Unix command line, where you can basically string together the output and input of text functions. For example, you can pipe the output of grep to awk, and then you take the output of awk and pipe that to sed, and so on and so forth. Well, toolz pipe is the Pythonic manifestation of that process. So it allows you to basically pipe the output of one function into the input of the other. So in this case, parents is a source for data, and it's fed as input for the first function, and the output of that function is fed as input to the next function, and so on and so forth. And the last function, its output's returned. So let's take a look at a sample, and we're not going to do all of them, of how these functions work. So let's look at tournament selection. So tournament selection takes that population, and it's like, imagine it's a vending machine where you just press a button and it yields an individual. So you see this infinite loop and this yield. That means that this is a Python generator function. So it will just keep on demand selecting two individuals by default, and it returns you the best one, or yields the next one to the next operator down the line. Next. So you take bit flip, it doesn't take a population. By contrast, it takes an iterator to an individual that's returned from the preceding operator, in this case, the clone operator. And all it does is it just zaps that individual with some probability and yields that to the next operator down the line. And again, that while true yield loop is an indicator that this is yet another Python generator. Next. And lastly, pool is the driver for this. This is the sink from the data source. And all it does is a list comprehension that just keeps calling next n times. And every time it calls next, it just pulls individuals through that pipeline. For those of you familiar with manufacturing, this is almost like a just-in-time framework. That as needed, it just pulls individuals through this pipeline and fills up this bucket. And once that bucket is filled, it returns that bucket as basically the newly minted offspring. Next. So one of the things I want to show you why this is so important, having these pipelines of these loosely coupled functions, is it allows you to drop in new pipeline operators and take out pipeline operators and even rearrange them, and they automatically hook up with the neighbors. So in this example, we took the previous pipeline and we added an entirely new operator. We added crossover. Now, again, you look on the right, and you see it's yet another generator. It's got that while true loop, and it yields, but it yields two offspring, because when you're selecting two parents, you're crossing them over, and you create two new unique individuals. So you yield those one by demand, depending ultimately what the pool operator requests. Now, I'll point out, this operator, it has double the appetite of some of the other ones. It needs two individuals. So that means that tournament selection and clone are now doing double the effort, but they are none the wiser. They have no idea that they're being called twice as often. And that's part of the appeal of this sort of loosely coupled pipeline approach, is it facilitates play. Because as researchers or instructors, you're going to want to play around with a pipeline to get some desired behavior. And again, this pipeline approach allows that. Let's jump into some real-world applications for how we're using LEAP right now at the Oak Ridge National Laboratory. These are works in progress. We're going to talk about two different applications. One where we're using LEAP to train spiking neural networks, and another where we're using LEAP to help train a convolutional network to drive an autonomous vehicle around. Next. So spiking neural networks are a type of artificial neural network that are actually more aligned with how actual biological neurons work. And so it's depicted, you see a spiking neural network depicted on the right. It has neurons as green dots. The yellow dots are input, the red dots are output, and you see these white dots flying around. Those are the spikes of different amplitude careening around the network. So those of you familiar with artificial neural networks and deep learners, the first thing you'll notice is there are no nice deep layers in this. You've got a lot of stuff that's careening around this at different times. It's just a giant hairball. So good luck applying a gradient descent approach to train this thing. But evolutionary algorithms are actually very ideal for training the parameters for a spiking neural network. Next. So that's what we're doing here is there's something called the F10th competition. And at ORNL, we're training a spiking neural network using LEAP to actually drive around in simulation, which you see on the right. You see this little dot flying around. As a simulated version of the car you see in the lower left, driving around a simulated track. And again, we're using LEAP to train this. And I believe the gentleman, Parker Mitchell, he told me it took 5 to 10 minutes on 20 cores to get the behavior you see on the right. He also developed this card you see at the bottom, this micro-Caspian card. It's based on an FPGA chip, and he's going to copy over this spiking neural network onto that card, drop the card into that car, and have the actual car drive around using the spiking neural network. And I'll point out that this card has a very low power requirement. It's only 10 to 20 milliwatts, and it's also very small. It's about the size of a credit card. So it actually has generalized applications, I think, to other areas. So we're pretty excited about this. Next. So another vehicle-related application for LEAP is training an autonomous vehicle convolutional neural network. We're using the Carla open source test bed, development bed that's developed for training autonomous vehicles. And on the left, you actually can see a video of a simulated Tesla car going through one of the Carla towns. Next. So let me tell you a little bit of how this works. So that simulation you saw, we have a robot. It's a perfect driver driving around these towns, and along the way, it's taking snapshots at regular intervals, training data, and accumulates about tens of thousands of these images that we use to train a neural network. Next. In particular, we're training it with Mendel, which is another evolutionary algorithm. It is an asynchronous steady-state evolutionary algorithm that I talked about earlier, and it's actually doing multiple jobs. It's training. It's learning, it's using an evolutionary algorithm to evolve the architecture, so the number of convolutional layers and the order, the associated hyperparameters, and it's using PyTorch to train the models. Okay, so after all this is a model that hopefully is a good driver, but then what we do next is we try to break it with something called Gremlin. So Gremlin is an adversarial evolutionary algorithm. So where Mendel is a maximization of a fitness, Mendel is taking the same fitness function and is minimizing it, is trying to break the model. Now, why on earth would Gremlin try and do that? So any of you guys are musicians and you're learning a new tune, you might run across a phrase that's challenging. So what do? You stop and you just woodshed that phrase. You just play that phrase over and over and over again until you've mastered it, and then you move on to the rest of the tune to learn it. Same principle here. What Gremlin is doing is it's finding specific scenarios where the model is struggling, and then we go back to the training data and add more examples of those scenarios, and then do the training cycle with Mendel all over again, hoping that the additional number of those bad scenarios actually improves its performance in that area. And then we repeat the cycle. Gremlin finds the next scenario that the model struggles with, and we just repeat the cycle over and over again. And the hope is that this process will actually improve the overall performance of the models. So Gremlin itself is also an asynchronous steady-state evolutionary algorithm. So this diagram should look awfully familiar, but instead of neural networks that we're tuning, these are just scenarios that we're trying to find where the worst scenario where this model is performing. Next slide. So what do the scenarios look like? So this is a town one. Carla supports several different towns. I'm just showing you the first one. We've taken a route. We've cookie cut it into 64 segments that are overlapping. So each segment is 37 meters long with 6 meters on each end overlapping. And we overlap them to make sure that we have a good sampling of the features along the route. And associated with each segment is the weather. How much cloudiness is this? What's the sun angle? What's the sun azimuth? How much fog is there, and so on and so forth. So the genes of each individual basically contain like the town and the segment and all that stuff. And we're just trying to find the right combinations of those so we can figure out which one of those combinations we need to create more examples of to continue the training process. So again, this is the work in progress, but this is one area where we're actually applying LEAP. Next.
All right, so quick summary of everything that we've talked about today. We've talked about trying to build features into this framework that are useful to engineers, educators, and scientists. We've built a syntax that we think is really nice and orthogonally designed. We've focused on distributed resources as one of our early features. We've shown that we can hook this up to OpenAI Gem and do reinforcement learning style problems with evolutionary algorithms. And we have a number of initial algorithms implemented and a few that we're working on right now and making good progress on.
So we mentioned Jeff earlier, and we would like to thank him again. Jeff Bassett was, again, the original developer of LEAP, and he continues to actually make important contributions to this version of LEAP. We actually meet every week and have like a scrum, and Jeff is a very active participant there.
And we're very grateful to Katie Schumann and Parker Mitchell and their team at Oak Ridge National Labs for letting us share some of the examples from their lab's work today, and for being LEAP power users, helping us refine its feature set against real uses.
Thank you, Mark and Siggy, for a very exciting presentation. It's great to see amazing content, great to see live demo, great to see cart poll. Any presentation in which you can actually see cart poll in action, I think, is a great presentation. There's a couple of really interesting questions in the chat, which I'd love to share with you. But before that, I want to comment on something interesting as well. It's more of a comment than a question, but I remember, and you mentioned, Mark, kindly that you use Dask to do the parallelization. I remember quite some time ago, I came prepared to this talk actually. So this interesting paper I had read from OpenAI researchers, Tim Salomon et al., and I've made that little green box in the algorithm 2 line 8, where they had come up with an interesting approach where instead of having to send the entire parameter for each sort of node back to all the other nodes so that they could then do some mutations and recombinations. What they did was came up with a very interesting trick where essentially they seeded all the nodes with the same parameter vector coming from, let's say, some master node, and then they knew what the random seed was in each of those nodes to do the mutations. And then when the mutations happened, they simply passed back the fitness function score back to back actually to all of the other nodes, and then all the other nodes could very quickly recompute in their own environment what the fitness function was and do the mutation. So very interesting that these kinds of interesting speed ups and techniques are being put together for the last 3 or 4 years. Your thoughts on that?
All right. Yeah, I think I've heard of this approach. I think actually it was Jeff Bassett in one of our LEAP discussions that brought this up. And I think it's actually quite clever. It's to put it lightly, it's sort of a clever abuse of the pseudo-random number generator, right? In a very clever way. And certainly something like that could be implemented in LEAP, because again, LEAP is meant really. It's going to sound strange. We were a little selfish in developing LEAP because we're researchers. And we were frustrated with what was out there, and so we wanted to implement things like that are kind of difficult to do with the existing evolutionary algorithm frameworks. So yeah, it should be easy to implement, or knock on wood anyway, to implement something like that. And again, kudos to the paper authors, because that was kind of a clever approach of leveraging the random number seeds like that as a way to scale up the algorithm.
Yeah, it's the kind of thing that could be. It's useful in applications where the network communication overhead during a distributed algorithm is a big part of the costs, right? And in some applications, that's a big deal. In other applications, it's not so much, because the cost of evaluating a simulation often dwarfs the cost of transmitting a solution. But that's not always the case. We have colleagues right now working with large neural networks tuning the weights, where you have very, very long vectors of solutions that need to hop around the network if you're doing it in a distributed way.
Yeah.
No, that's absolutely right, Siggy and Mark. And I know, Mark, your colleagues in the cryptography team are probably not comfortable with using random seed generators, especially if they're being used to generate cryptographic keys. But that's a whole separate topic for a separate conversation. There is a couple of really good questions from Imeric V. He's asking questions around how easy is it to create customized operators, and what would be the advantages of LEAP over existing libraries, e.g. DEEP?
Okay, I can definitely answer this. So I mentioned Parker Mitchell, and he used LEAP to train the parameters for that specking neural network. And so one of the things that he wanted to do was to speed up LEAP. We're just using regular lists of like numbers. And one of the clever things he did is like he changed the representation to use NumPy, which is really kind of a C++ representation for numbers. And that yielded a significant speed up for LEAP. But that meant he had to write new operators that could use that representation. And he gave us feedback. He's one of our first guinea pigs, and he told us that it was very easy to write new operators, which was a great relief to us because, of course, Siggy, myself, and Jeff are deep in the weeds of LEAP, so it was actually good to kind of get validation from what we call the triumvirate, they're actually able to use LEAP effectively. And the question, what was...
Yeah, the other part was, how does it compare to things like DEEP?
So DEEP uses Scoop, which is basically sort of that MapReduce model. So they fan everything out. It's that byte generation approach. And I wanted to use DEEP, but again, when you're scaling up to a machine like Summit, you can't go with that MapReduce approach. You need that asynchronous approach, and currently DEEP does not support that. So that was one of the strong motivating factors. Is I didn't want to waste time on the Summit. I wanted to make the most efficient use of the resources there. So an asynchronous approach was best, and DEEP doesn't support that as far as I know.
And more generally, there are certainly other EA frameworks out there that have been used in the research community, and we've all got experience with a lot of them. So all three of us who developed Leap have been core contributors to ECJ, which is a very popular one in the Java world that's been used for decades now. But really, we kind of came to feel after many years of using these other frameworks that we kept running into cases where the design constraints of a particular framework, the assumptions that each framework makes, made certain things difficult to us. So we think that in Leap, we've gotten something that's a little more general and easier to learn. And you mentioned adding an operator. Usually that's as simple as writing a short function and just plugging it into the pipeline. There's very little boilerplate involved in extending Leap and adding new features. So.
That's great, Mark and Siggy. So I'm going to go a bit out of sequence in the questions and pop this one in the queue. So while we're on the topic of operators, how difficult is it to create these custom pipelines, and also how difficult is it to create custom operators?
Well, again, the custom operators should be fairly easy to put together, and the operator pipeline is also easy to put in operators, including your custom operators in any particular order. There are some gotchas in that you have to make sure that some of the operators match up with one another. So this is why I did the sample, the 3 different flavors of operators to show off the 3 different kinds of major flavors, right? One takes a population as input. Another takes an iterator as input. Another has as output a sequence or a collection of individuals, and so on and so forth. So I didn't have time in the talk, but you notice there were some decorator functions. So actually, Siggy wrote some check functions to basically check and make sure that the input and output of your operators match up, so that you get actually a reasonable error. So it should, for new folks new to Leap, it should hopefully minimize the learning curve of actually implementing new operators if you use these decorator functions.
And one thing that we've learned from using this design is that the pattern of using a list of operators with some kind of standardized interface, and then being able to write just a simple Python function to plug in to add new operators is a really general and powerful design pattern. So I found myself almost automatically, once we had this proof of concept kind of fleshed out in Leap, saying, well, hey, we can use this same pattern for other kinds of algorithms. So I've built a couple of agent-based modeling simulations using this pipeline method, where you have one operator that advances the state of the agent-based simulation, another operator to update a visualization, another operator to collect statistics. And it ends up being this elegant way to kind of plug in components to create a simulation experiment in new environments and have it all visible in one kind of master view of the algorithm. So it's something that we're seeing usefulness for in our other projects now that we've gotten experience with it here.
Okay, that's great, Mark and Siggy. Thank you for that answer. Another question here, this one's from Mariana, who's asking a question around, are you familiar with uses of EA for medical or healthcare type scenarios and settings?
Yes, absolutely. So one pertinent example that comes to mind for me is at MITRE Corporation, which I work at. There's been a group that has developed a synthetic data set generation technique called synthea, where they've built synthetic population information about the history of patients that's completely de-identified and built out of probabilistic models that were themselves calibrated on real patients, I think, in Massachusetts. So it offers a research base for people to work with data that can be freely shared across organizations. And one problem that they've stumbled on there is that while this approach has been very effective for the population they built the system for, generalizing it to new populations that they want to create similar synthetic data for can be very, very labor intensive to tweak the probabilistic models that define how likely somebody is to get cancer given these other risk factors over the course of a patient's life trajectory. So they're doing experiments right now with how to use evolutionary algorithms to automatically calibrate models for synthetic data set generation is one example that I'm familiar with. Okay,
great. Mark, anything from your side?
So I'm not as closely tuned to the medical community, because at Oak Ridge, a lot of our models have the tendency to do with autonomous vehicles, particle accelerators, and that sort of thing. But I do know that there are active areas of research of using evolutionary algorithms and applying them to the medical community. In fact, I think there's even a workshop at some of the major evolutionary computation conferences. There's two big conferences. One's called GECCO, the Genetic Algorithms and Evolutionary Computation Conference, that's run by ACM, and the other run by IEEE, the Congress on Evolutionary Computation. And both of those have active tracks of where evolutionary algorithms are actually applied to medical community type problems. Mm-hmm. So I know there's a rich set of references that are out there.
Okay. Thank you both, Siggy and Mark. We are coming close to the top of the hour, so I want to thank you sincerely on behalf of the Synthetic Intelligence Forum for making time in your busy schedules and sharing with our community all the details, the interesting kind of tidbits around LEAP. And I'm sure that we'd love to have you back in a couple of months when LEAP has evolved and leapt forward, if you will. And happy to have spent this hour with you. And thank you again for making time in your schedules to come and talk to our community. Thank you so much.
Thank you, Vic.
Yeah, thank you very much.
Bye for now.
All right, take care.